is Logan's question earlier about, or somebody's question earlier about tests and such. It was you, wasn't it?
Yeah, it was.
Quest.
So, yeah, it's a quest. I can't remember if it's a quest or a test right now. I'll have to look.
It's a quest.
Is it a quest? That's what it says. So that's on Thursday. It's over the unit. I guess it would be 5. So chapter 6 stuff on differential equations, slope fields, solution curves, and logistic, right? And so what I had said in the calendar and on Schoology, I had set Wednesday up to be a review day, especially since logistic is in there, and that's a new thing for sure. And so if we don't end up having school on Wednesday, we'll still have a review day on Wednesday. Like we said, it'll just be in the comfort of your own home or wherever you happen to be. So then we'll plan on the quest on Thursday. You guys remember the rule about a quest? Like how it's handled? Yeah, so does it go in the test category? Does it go in the quiz category? I don't know.
Helps you best.
It depends on whichever one is going to help you more or hurt you less. Hopefully it's the help you more option. Does that make sense? Okay. All right. So we are going to spend one day here today talking about area. There was a little intro video about this. And so I've kind of fast forwarded to the part that's not the intro video. Feel free here if you want to use your graphing calculator to visualize what this region or regions looks like. And once you have the visual kind of set, you think you know what it looks like, see if you can set up an integral to help you find the total area enclosed by these two graphs, and then see if you can run it all the way through. See if you can actually find the value of that integral to get a numerical answer to the what is the area. So please avoid using Math 9. Have we talked about Math 9 in here yet? Yeah, we have. Yeah, we totally have. Avoid using Math 9. But use the calculator to graph. Set it up on paper and pencil. We'll check in a second.
Check our work with Math 9 on the
Sure. Yes.
Other team. So our first day is pretty easy because they're seated good. Then the second day, if we win our pool, we cross over with whoever wins the pool with Rampart, Grandview, and one other team. So it'll probably be Rampart. So we'll play Rampart on the second day, and then I don't know what happens after that. But.
And Rampart's been ranked in the top 2 or 3 the whole season, right?
Well, now we're ahead of them.
Oh, you're
They're
ahead?
6, we're 4. Chapa's 1.
Nice.
But they're seated
Did you guys play
us.
Chaparral?
No, not during the regular season.
Okay.
But Rampart's seated ahead of us at Shine Mountain, so technically if we lose to them, it wouldn't drop our RPI.
I see.
Okay.
Because that's like where they.
But hopefully we beat them. That'd be nice.
Yeah. That's a fun tournament. They do such a good job getting a lot of good teams there.
They do. And it's always like, they always do a great job just running the tournament too.
Mm-hmm. So I don't know how far you guys have gotten. I decided that after I graph this, my goal would be to find intersection points because we're talking about area that's at least in part bounded by these two graphs. And so I figured if I could find the x values for right there and right there, that might help. So did you guys do the same thing? Or did you think of that maybe?
Honestly, I used the integral and I thought those were intersection points, not.
So I think this is going to be pretty important here because this is -2 over here, and that's 1 over there. We're already told that we're supposed to find the total area bounded by those graphs on the interval from -4 to 0. So isn't -4 over here somewhere? And so if I were to, continue this parabola on down here a ways, wouldn't there be another part of the area defined by, oh, come on, there we go. That.
That just sucks.
So not only would I have this green area right, oh wow, too much. I'd have this green area right here, but then I'd have this orange area right there. And what's so tricky about this is that for the green area, isn't the red graph higher than the blue graph? But then when you look at the orange area, the higher one and lower one flip their relationship. So I would encourage you to think about this. Whenever you see this phrase, total, like specifically the word total area, that's probably indicating that somewhere along the interval that they've given you, the high function and the low function have switched. And you're going to have to consider both. Because, I want you to think about this. If all I did was, please check out this expression. Let's talk about what would happen. If I did the integral from -4 to 0 of f minus g, what would actually happen here? What would I be finding? Anybody know? If I just set it up just like that. Okay, well, let's do this. Now, I would encourage you, what I'm writing down right now, please don't write it down. What about, please don't write this down. This is not where we're going with this. So, the integral from -4 to -2 of f minus g, what kind of number would that be?
Negative.
It'd be a negative number. Mm-hmm. What kind of number would the other one give us? Positive. Yeah. So if I were to go back here and look at that, what would be I'd get some answer, I'd get some number for this. I have no idea what it is. What would the meaning of that answer be? Say again?
Is it just find the area, not the total area?
It does definitely still has to do with area.
It's just the integral instead of the area.
Right, and isn't the integral just simply going to add up whatever you tell it to add up? And in this case, I'm telling it to add up f minus g times dx. So what would that be? It definitely would not be the total area. And I don't think we can just say the area either, because there is no just the area, because there's two different areas, right? Any ideas?
It'd be that top, the green area minus the orange area.
Yeah, it'd be green minus orange. Yeah, so I think that's a pretty good explanation. Wouldn't it simply be the difference between the areas? It might be a negative number, depending on the order of the subtraction, how that works out numerically, but it would simply be the difference between the areas. So this, I think, why the graph is super duper important. The graph would allow us to see all that relationship happening and then allow us to set up the appropriate integrals and so on. And so I think I would go with something like this. The integral from -4 to -2 of g minus f dx, right? Line minus parabola, because line's higher, plus the integral from -2 to 0 of f minus g. Because once you get to that other interval from -2 to 0, that's when you're going to get the parabola being the higher of the two graphs. So this one requires a split up And I think that word total is your big hint. Total area means there are probably going to be a switching of relationships between the graphs. What do you guys think? That's the big conceptual piece. The rest of this is largely procedural. Doesn't mean that it's easy, but how are you doing with the concept? Any questions? Okay. Okay. Well, I'll just kind of quietly work here. Maybe we can compare our answers. Hopefully I have enough room to do this. So I've got some antiderivatives up there. Hopefully not surprisingly. The antiderivatives are the same but opposite, right? They're the same terms but just different signs. So let's see here.
This is where leaving it in the arithmetic really helps in the AP test,
What about arithmetic?
where you don't have to like condense everything and you can just write the numbers.
Let's talk about that. Yeah, that's a great point. I think that's worth talking about here in a second. Huh, yeah, maybe this is where I will stop. Right? So, I hope we can all do our antiderivatives, just a bunch of power rules. And then I evaluated from -4 to -2 and from -2 to 0. And to Logan's point, really technically, and I'm really no different. I mean, if your answer is that, and as long as we have all the arithmetic at that point correct, I think we're good. I don't see any super compelling reason other than just curiosity's sake to go through and get a common denominator of 3, right, and add everything up. You could totally do it. But from a testing perspective, I'm not going to make that a thing. I'm not going to make that a thing here either. So I would say you'd want to be super duper careful. Why would the red box not be okay, but the gray box is? Where's the final answer? Yeah. Isn't going from gray to red part of like the fundamental theorem of calculus? So you can't leave off any calculus steps, but if the only thing, the way I like to put it is, if the only thing left is something that like a decent 7th or 8th grader could handle, you're definitely okay. And hopefully they could add fractions, right? Hopefully we can, but we don't have to.
So would this be acceptable if I left it with like exponents and stuff?
Yeah, I did a little bit of work in my head, right? I said, 2 squared is 4, half of 4 is 2. Oh yeah, yep, totally fine.
But I'm good to leave it there.
Yep. Yeah, I think it's a good strategy. Okay, how are we doing? All right, fair enough. So please then take a look at number 3. And do they, in number, like in pre-calc, do they still do this? Where you graph like functions where x is a function of y instead of y is a function of x? I mean, do you remember doing like sideways parabolas and sideways cubics and that kind of thing? Remember that? Did you do that, Aiden, in pre-calc?
I don't really remember doing that, but.
Okay. Well, then let's do this one together. How about, because this one's a little bit weird for sure. So it says sometimes it's easier to use a horizontal rectangle, unlike the video I used verticals, and there we just use vertical. When we do this, the representative rectangle would be dy wide. I'll show you an illustration of this. And because of this, the variables in the integral and the limits would have to be, they have to all be y's, right? So dy or dx is really what tells all of your variables and numbers what they have to be. And so let's graph this, then we can talk about what the higher function is and all that good stuff. So do y'all recognize that the first graph is a parabola? But it's not a classic parabola because it's not y equals x squared. It's x equals y squared. So how will this parabola open? It will open to the left. Yeah, it'll be a left-right parabola. And let's talk about how it's going to be affected. So it's opening left for sure. And what does the 3 do to the parabola?
Horizontal shift.
Shifts it right. That's right. So this would be right 3 opening to the left. So to the best of my abilities, I think it should look something like this. Man, I always get that first half pretty good. Second half looks terrible. We'll just go with that. Okay. And then the other one, x equals y plus 1. Everything gets flipped around here as far as slope and y-intercept. I mean, so if you just have a line like this, I've always felt like it's easier just to subtract the 1 over and get y equals x minus 1. So I think the graph of this would look about like that. Oops, it's got to be down 1. How about that? Okay, so can we talk about ways you could do this? I just want to throw this out to you. If I was absolutely determined to use a vertical representative rectangle, I could, and please don't write any of this stuff down because I don't think this is best, but check this out. Okay, so if I wanted to use a vertical representative rectangle, I could think about representative rectangles like this. And the truth is, with all those representative rectangles, they would all be dx wide, and then wouldn't their height be based on essentially a y value minus another y value? Does that make sense? So somebody might be really tempted to do this and say, I just want to use x's, so I'm going to go with vertical representative rectangles and dx's, and it's all going to be the way that it normally is. But then do you guys know where you'd run into some issues, like some serious issues that you'd have to really be careful with? Yes, as soon as you get to the intersection point, things will very much change nature. You will get these blue representative rectangles over here. And what's different about these, of course, is that the green representative rectangles, their height is determined by the red graph minus the blue graph, right? But then when you get over to those light blue or royal blue rectangles, no longer is the red line telling those rectangles how high to be. Now it's just blue parabola on the top, blue parabola on the bottom, and how do you handle that? Well, of course, that's going to, like when you try to solve this, like if you did x minus 3 equals negative y squared, 3 minus x equals y squared, when you square rooted both sides, what would you get? Plus or minus, and all of a sudden that plus or minus is going to come into play, and you're going to have to think to yourself, wow, how do I handle the plus and the minus? Can I double it? I mean, you're going to have to do some pretty heavy-duty thinking, and there's nothing wrong with you doing heavy-duty thinking, but I'm just thinking to myself, if there were an easier way to do this, why wouldn't I just do that easier way? So let me show you what I think would be the easier way. Right here, let's make all those rectangles go away. And if I, instead of going with those green and blue rectangles, what if I just went with this lovely pink rectangle, like so? Do you notice that no matter where I draw in the pink rectangle, you notice how every single one of them is the length is determined by the blue graph and the red graph. There's no transition point. There's no place where I have to switch over to a brand new integral. I can just say they're all pink rectangles, and I just go with that. That make sense? Okay. So if we did draw something like this, what would you guys say is the higher function?
3 minus y squared.
Yeah, isn't it the one on the right? In this case, that's the parabola. So I'm going to go integral of high minus low. The thickness of each rectangle is now dy, because the thickness is measured on the y-axis scale. The only issue I have left to work out here really is my limits of integration. Where would I start accumulating these rectangles and where would I stop?
The lower intersection point.
The intersection, yeah. The intersection points, again, will matter. So maybe I come off to the side and I do my intersections like so. This would be 0 equals this plus this. Yeah. We can see pretty quickly that it's going to be -2 to +1. Okay, and then as far as what you do from here, if the calculator is active, you use Math 9. If the calculator is not active, you do basically what we did in number 1, get a nice numerical answer, and you leave it be. What do y'all think? Any questions? Okay, I wanted to go a little bit faster through that one since we have a shorter class. So let's do number 4. It's our last one. It is calculator active, so certainly want you to look at the graphs of these, figure out what the region looks like, and then I suppose in number 4, if you want to use Math 9, go for it. Make sure that you're writing stuff down that you need to. But check out number 4. Veterans, you guys have been doing remarkably well with all of our brand new stuff, right? The improper integrals and logistics seems like you're doing pretty well. Just be reassured, there is one new topic in this unit. It's not all just area and volume. We're going to be looking at arc length. So, you know, if somebody asked you how long a line segment was, wouldn't you just use the distance formula? But what if somebody asked you how long a part of a parabola was? It's a little different, right? You still use the distance formula, but you've got to use an integral. What if somebody asked you to find out, you guys know how sine does this? Like one period just goes up, down, up, down, up. What if somebody asked you how long is sine? Now what's the area? What if you had to figure out how long that curve was? Like if it was a string and you could just like straighten it out? Use a ruler or something? That's what we're going to do. So maybe stuff you never thought of, maybe stuff you did think of and just never knew how to do. We'll do that coming up in this unit. So we're working on number 4. Hopefully we get a nice graph going and figure this one out. I think I know what this looks like. This is interesting. I'm just going to peek here.
Just in my window.
Oh, you must have a huge window.
Yeah, something left
Or
over
pretty
from
large.
last time.
Yeah. I bet you Zoom 6 will work pretty well.
Yeah.
What is this? What's the horizontal? That should be y equals 1. Yeah. You should have that 2e to the x. Oh, that's not even turned on. You need to turn. Oh, okay. Yeah, that last one should be a vertical line. Okay. So it's piecewise. I've tried to represent that piecewise up there with colors. Does that make sense? Mm-hmm.
But it doesn't like create a smooth line coming off of 2e to the x.
Oh yeah, it should be, well, I didn't represent that very well. It's continuous though, right?
Yeah.
Yeah, I'll try to fix my not very good representation. Oh, there goes my line. Let's see if I can do a little surgery here. So how about that? Is that better?
Yes.
Okay.
In my brain.
Yeah, I think it's fair. Looks about like that. Yeah, you can tell, you can like do a mental quick check. You can see that it's definitely continuous there as it around 0, but the slope from the left should be 2. Slope from the left should be 2, but from the right the slope would be 0.
Okay.
So yeah, agreed. So we're looking for the area of the region here. I'll make it orange. So looking for this orange area. Can you guys, as you started to consider setting this up, do you guys think it would be wise to use dx rectangles or dy rectangles? Dx would be the vertical ones, dy would be the horizontal ones. You say dx? Why would you say dx?
It just keeps increasing.
It just keeps increasing.
Like as you go from left to right, you don't have to like change that.
So dx rectangles would look like these green ones. What do you guys notice about all these green rectangles? What's that?
I said they're green.
They're green, yes, that's true. Well,
They're like touching, like in the function above was touching the same function twice the parabola. It's not doing anything.
okay. Isn't there a transition though?
Oh, he's getting.
There is one transition, right there at x equals 0. We would transition from blue to purple for the top. Let's see what the dy rectangles would look like. Dy, it's a little more complicated. Sam, in the end, I think I agree with you. Because if I did dy rectangles, how many transitions are here? There's 3, right? So the vertical line is always the right edge, but at the up on the upper part, isn't it purple for the left edge? And then as you drop down, then it's blue for the left edge, and then finally it's red for the left edge. So basically it's a question of, do you want to do 2 separate integrals for the one transition, or 3 separate integrals for the 2 transitions? You could do either one, but since those functions are already in terms of x, stay with that, right? That makes sense? Okay. Cool. I didn't really like that one green. We'll go with this green. Okay, so how about these for rectangles? Okay, so any volunteers on sharing what you did for your integrals?
Is it okay if I'm probably completely wrong?
Yeah, it's always okay.
Wrestling is
It's just class. This is not a test.
You're
Never
not
okay,
Santi, so
Logan.
it's okay.
I am recording, so he'll be able to hear that loving comment.
If you watch it, that's how
That was Aiden.
So I did mine in terms of x.
Yeah.
So I found the intersection point between y equals negative x and 2e dx. So right there.
Yep.
And it's negative 0.853. And then the right bound is really easy because you just plug x equals 1 into x squared plus 2.
Sure.
It's 3.
Okay.
So there's your bounds, and you're gonna set up two separate integrals, each one going from each one of the bounds to 0.
Oh, wait a minute. You said. Oh no, this is x equals 1. Okay, this is x equals 1.
It's x equals. Oh yeah, it is x equals. Sorry, I overcomplicated that.
Y is 3.
Yeah.
I'll give you that. Yeah.
Um.
Okay, so you said two separate integrals.
Yeah, it doesn't change a whole lot. It just changes one of the bounds.
Okay.
It's the same integrals though. And I just did from negative 0.85 or from 0 to negative 0.853.
Or you. So do you mean this, or should I write them the other way?
I meant that. Yeah.
Okay.
And 2e dx minus negative x dx plus from 1 to 0.
You mean 0 to 1?
Yeah.
Okay.
Yeah. It makes sense.
I just want to make sure. I want to represent you correctly.
Yep. X squared plus 2 minus negative x dx.
And that's it.
Very good.
You guys agree with him? Hope you do. It's really well done.
Thanks, guys.
That was extremely well done. So since this is a calculator active question, what would you be doing now? Math 9. Did anybody go there?
Yes.
What did you get, Sam?
3.617.
You guys agree with Sam? Fantastic. Okay. Really, honestly, that's it for area. Let's rehash though. Let's make sure that you understand. Like in this situation, you might be forced to have a transition point. You might be forced to have two separate integrals, so be ready for that. You also might have a situation where dy makes it easier, so be ready for that. And then you also might see a situation in which you have to find total area, in which you're going to have to split up based on intersection points and whichever one is high, and then later on the other one's going to be high, or could switch twice, who knows. So be aware of those things there. Otherwise, I think we're good. Wouldn't you feel silly if they'd called a snow day today and you look out there and you see that? Wouldn't you just feel silly? It did. It
Yeah.
did.
The way to school was pretty bad.
An hour and a half later, because like the
No, what
roads
you
were
do is you
so
trust
bad.
and you take advantage of your new conditions.
I thought, at least in my
You
neighborhood.
get in a wreck and
The roads
see
were
school.
the roads were.
I'm glad
actually
you didn't
really
get into a
bad.
crash.
Ever
Like,
get e-brake
two of
in
my
snow
neighbors on
before?
my street, I don't
Like-
have like the brakes, but it's off.
Well, that just shows you were going slow enough. You were going slow enough. You made it.
Yeah,
And
and I
my
didn't
car
know.
is just really not the best in snow at all because it's
Oh
not
man.
cold.
All right.